In this example, we're told we have a rocket engine designed to operate at a pressure ratio, which is defined here as the inlet reservoir pressure. So that's the stagnation pressure, to back pressure of 37. And we're asked to find a number of things. The ratio of the exit area to the throat area, which is necessary for the supersonic exhaust to be correctly expanded. That's an important phrase. Correctly expanded means perfectly expanded or at design conditions. We're also asked to find the Mach number of the exit flow under correctly expanded conditions, again at the same conditions as A. The lowest pressure ratio at which the same nozzle would be choked, and the pressure ratio at which there would be a normal shock wave at the exit. And we're told to assume a specific heat ratio of the gas of 1.4. So just let me make a note of this. This 37, this is the stagnation pressure to the back pressure. Okay, so let me just sketch this out. Since we're talking about supersonic exhaust, I'm going to just sketch it as a converging diverging nozzle, starting from a reservoir, which is at stagnation conditions. And then the flow would have to go through some throat, where we reach a Mach number of 1, and then go supersonic in the diverging section. And then this would be the back pressure. This is the exit. Okay, so we're told that the flow is perfectly or correctly expanded, so that corresponds to the following. You'd have to refer back to the notes for this, but this is a plot of the pressure over the stagnation pressure, upstream stagnation pressure, this pressure right up here, plotted as a function of position along the nozzle. Here's where the throat is. Here's where the exit is. There's a ratio of 1. So for one other thing, here's P star over P naught. So for correctly expanded conditions, it corresponds to this kind of a situation. What's happening here is the Mach number is subsonic in the converging section. It reaches sonic conditions at the throat, and then it goes supersonic in the diverging section. And then when it's correctly expanded, it means that the exit pressure and the back pressure are exactly the same. And you have supersonic flow at the exit. Okay, so that's the case we're looking at here. Since I know that the exit pressure and the back pressure are the same, and I'm given what the ratio of P naught over PB is, and I know the flow is all isentropic for this scenario, I can simply use the isentropic relations to find a number of items here. So let me just write that out. So PE over P naught for this case, for correctly expanded conditions, is the same as P back over P naught. And that'll be 1 plus K minus 1 over, oops, that should be a minus. 1 plus K minus 1 over 2 at Mach number exit squared raised to the K over 1 minus K. So that's just the isentropic relation. And I can write this out because I know that the flow is all isentropic through here. It goes from subsonic, sonic, supersonic, all the way to the exit, and it's correctly expanded. So the exit pressure and back pressure are the same. That's how I got away with that. It's all isentropic, so that's how I can write this expression. And from here, I know that the back pressure, and I know the back pressure to stagnation pressure ratio, that's all equal to 1 over 37, because that was given. So I can solve then for the Mach number at the exit. And if I do that, the Mach number at the exit comes out to be 3.0. So we have a supersonic flow as expected. So actually what we just did is we solved for part B first here. Once I have that Mach number, I can calculate some other things. Namely, I can go back to part A and find the ratio of the exit area to the throat area. That I can also use the isentropic relations for that expression. That's the AE over A star. Since I have a Mach number of 1 at the throat, that's right here, I know that A star is the area of the throat. Right? So this expression looks like the following. This one, there's a lot to write out, so just give me a moment. Okay, so there we go. So now we can solve this equation to find the area of the exit over the area of the throat. So all we need to do is plug in our Mach number of 3 Here we know the specific heat ratio of the gas is 1.4, so I'll just write that here, K equals 1.4. We can now solve this for AE over area of the throat. And when we work that out, that comes out to be 4.3. So that means we need this area here to be 4.3 times larger than that area in order to have these conditions. Okay? So that does part A for us. Now the next question is, what's the lowest pressure ratio, P naught over PB, at which the same nozzle would be choked? So the choked flow conditions occur when going back to my plot over here, choked flow conditions would occur just when we reach a Mach number of 1 at the throat. So the time when that first occurs will be when we have the following flow. It's subsonic, sonic, and then it goes subsonic again. So it kind of follows this curve. So here the flow is subsonic. It all stays isentropic, so it's isentropic here, reaches sonic conditions, goes subsonic and stays isentropic again. And since the flow is subsonic at the exit, that means that the pressure at the exit will be the same as the back pressure. Okay? By the way, just I guess I'll note it here that pressure at the exit there is also equal to the back pressure. So that's the case I want to look at now. Now, in order to find that one, I want to, I know that the pressure at the exit is equal to the back pressure. And what I'm trying to do is actually find that ratio of P naught over the back pressure. So I want to know what that back pressure is. I already know. So that's what I want to try to find. The way I'm going to find that is I can, I now know A at the exit over the A star, right? We just found that for a moment ago, right? So we know the area of the exit over the area of the throat. The throat is still A star. So this still holds, this is still our AE over A star. But what I want to do now is I want to solve this for the Mach number at the exit. Now, if you go back to the notes, what you'll see is that this equation is double valued. That for a given AE over A star, there are two values for the Mach number that can give you that same AE over A star. One of them is supersonic, that's this one. Now what we're trying to do is find the subsonic case. So now what I'm going to do is I'm going to solve this equation, but solve it for the subsonic Mach number at the exit. And when you do that, that comes out to be 0.14. Okay, so that's now our Mach number at the exit for this particular case. And you can see it's clearly subsonic. Okay, and then to find the area, to find the pressure ratio, what I can do is use the isentropic relations. Because the flow is all entirely isentropic for this case, right? So it's subsonic, sonic, subsonic again. It's all isentropic. I now know the Mach number at the exit, so I can get PE over P naught. So I can solve for that. And that comes out to be, I guess I solved it upside down. So let me flip it around. You can solve that for P naught over PE, because that's what's asked for in the problem. But if you do that, that comes out to be 1.01. And just keep in mind that the exit pressure is the same as the back pressure, because the Mach number at the exit is subsonic, so the exit pressure and back pressure are the same. So that's why I can write that. So that's now our answer for this particular part of the problem. We're trying to find what's the lowest pressure ratio at which the same nozzle would be choked. So that's this case here, and that's what we just solved for. Okay, so that's our part C. We've taken care of that. The last question is, what's the pressure ratio at which there would be a normal shock wave at the exit? So for that case, what we have is a shock wave right here at the exit. Let me call this 0.1 and this 0.2 here. That one's a little more involved. So one of the things we need to notice is that the flow just downstream of the shock, so P2 here at the exit, that will be a subsonic flow. And so since it's subsonic right at the exit on the downstream side, it'll have the same pressure as the back pressure. Right? So that's one piece of information that we need to know. The other item is right upstream of the shock wave at state 1 here. We're still right at the exit, right? This is infinitesimally thin, the shock wave. So the Mach number leading into the shock wave will be supersonic, and so that Mach number will be this same Mach number. Right? So we know the Mach number at 1. So let's write this down. Mach number at 1, at the exit 1, is the 3.0. So it's just upstream of the shock wave right at the exit. We found that previously in the problem. Oh, by the way, just to sketch this one over here on this plot, the case we're looking at now is this. What's happening is the flow is subsonic in the converging section, reaches sonic conditions at the throat, goes supersonic all the way to the exit, hits a shock wave, and then goes subsonic. So on the downstream side, the Mach number at the exit is less than 1. On the upstream side, the Mach number at the exit is supersonic. So that's why it's 3.0. It's just the same as this first case we looked at, where the Mach number is equal to 3. But when we go through the shock wave, it goes subsonic. And then because it's subsonic there, the pressure on the downstream side of the shock is equal to the back pressure. Right? Because it's subsonic here, so that the exit pressure PE2 is the same as the back pressure. So that's the case we're looking at now. All right, so since we know the Mach number just upstream of the shock, we can use the normal shock relations to find the Mach number on the downstream side. So Mach number on the downstream side of the exit shock wave, we can find that using the normal shock relations. So let's write that out. So there we go. So we can solve that for the Mach number on the downstream side of the shock. It comes out to be 0.475, so it's subsonic as we expected. Now to find the pressure ratio, what I'm going to do is first of all use the isentropic relations on the downstream side of the shock. So I'm going to do PE. Well, actually, let me go ahead and do the isentropic stagnation pressure ratio on the downstream side of the shock. Let me write it out and then I'll talk about it. So here's the isentropic relation just on the downstream side of the shock. Here's the Mach number on the downstream side. The thing that I want to point out is this ratio. This is the pressure on the downstream side of the shock divided by the stagnation pressure downstream of the shock. Remember that the stagnation pressure decreases across the shock wave. So I have to be careful. I have to put P02 here because that's the stagnation pressure on the downstream side of the shock. So I can find that ratio. If I work that out, I'll get PE2 over P02 comes out to be 0.857. Okay, so that's only part of the puzzle here. Let me do now. The problem is I don't know the P02, right? So in order to find that, I'm going to use the normal shock relations to find the ratio between P02 and P01. P01 is the stagnation pressure upstream of the shock. So that's the stagnation pressure up here. Okay, because we have the shock wave P01, it's the same stagnation pressure and stagnation. There's the stagnation temperature upstream here. It's the same P01 as what we have here, and then it'll be P02 here. So that we can find from our normal shock relations. This one's kind of a longer one to write out, so I'll write it out just for completeness sake. Just bear with me while I write the whole thing out. Okay, I think I've written that out correctly, so we can solve for that. And so that gives us P02 over P01 is equal to 0.327. So you can see the stagnation pressure drops across that shock wave. So what I'm going to do now is I ultimately want to find what the back pressure to the upstream stagnation pressure is. So I'm going to take a ratio here. So P01 over PE2. Remember, PE2 is the same as the back pressure because it's subsonic just downstream of that shock wave. That will be the following. So I just need to combine these ratios together properly. So this will be P02 all over PE2. That's this expression just flipped upside down. And then I'll multiply that by P02 over P02. That's this expression flipped upside down, right? And then you'll see that the P02s cancel out. So if I do that and work out the numbers, this will come out to be 3.6. So that's the last part of the problem that we were asked to find, was what is that back pressure, the upstream reservoir pressure to the back pressure that will give us this case with a normal shock wave right at the exit. Okay, so if we have that ratio of stagnation pressure upstream to the back pressure with this given geometry, we will get a normal shock wave right at the exit there. It'll correspond to this case. Okay, so this problem, actually, there's quite a bit to it. Hopefully you understand all the bits. It's really a combination of just knowing how to use the isentropic relations and the normal shock relations together. All right, we'll end the example there.